Hi everyone. In this video, I'm going to walk you through the Label Radar Signal Labeler in MatLab, an essential tool for labeling and analyzing radar signals. Let's start. Contents. Introduction. Next, in Import Data into Signal Labeler we will cover. Define labels. Create custom auto-labeling functions. Label waveform type, PRF, bandwidth, duty cycle, and pulse width. Validate labeled signals. Export labeled signals. After that, in supporting functions we will cover. Compute PRF function. Compute bandwidth function. Compute duty cycle function. Compute pulse width function. Finally, conclusion. Introduction. This example shows how to label the main time and frequency features of pulse radar signals. This step facilitates the process of creating complete and accurate data sets to train artificial intelligence (AI) models. Signal Labeler eases this task in two ways. In manual mode, synchronized time and time frequency views help you identify frequency features such as the waveform type, which can be rectangular, linear FM, or stepped FM. In automated mode, you can register functions that measure the pulse repetition frequency, PRF, pulse width, duty cycle, and pulse bandwidth and only correct mistakes instead of labeling all signals from scratch. A built-in dashboard helps track the labeling progress and assess the quality of the labels. Import data into Signal Labeler. The radar signals in this example are stored in individual MAT files. Each file contains a data variable X and a corresponding sample rate variable Fs. Open Signal Labeler. First, on the Labeler tab as shown in Figure 1, then, next click Import and after that select from folders in the members list. In the dialog box, select the directory with radar signal files. To specify the signal variables that you want to read, click Specify and enter X. Add time information. Choose the Working in option and select time from the list. Select sample rate variable from file in the list and enter Fs. Click Import. The imported files appear in the labeled signal set members. Plot the first three signals by selecting the checkboxes next to their names. Let's take a look at the Signal Labeler window displayed on the screen. In this window, you can see the various components that make up the Signal Labeler tool. On the left side, we have the Label Definitions panel, which allows you to define the labels that you'll be applying to your signal data. You can create labels for different characteristics such as waveform type, pulse repetition frequency, PRF, bandwidth, duty cycle, and pulse width. Below that, in the Labeled Signal Set Members section, we can see the list of signals that have been loaded into the tool. Each signal is represented by a row, and you can expand each one to view its components, like the real and imaginary parts of the signal. The signals are also color-coded, which makes it easier to visualize and distinguish between different sets of data. The top right section shows the signal plots. Here, the real and imaginary parts of the radar signals are plotted against time. This visual representation is crucial for understanding how the signal behaves over time and helps in identifying important features. Finally, notice the export option on the top right. Once you've labeled your signals, you can easily export the data for further analysis or use in other projects. Define labels. Create a label definition for the signal waveform type. Click Add on the Labeler tab and select Add Label Definition. In the dialog box, specify label name as waveform type. Set label type to attribute and data type to string. Click OK. Repeat these steps to create attribute label definitions for PRF, duty cycle, and bandwidth. Modify the label name for each and set the data type to numeric. Create a region of interest, ROI, label for pulse width that corresponds to the regions showing initial and final crossings used to compute each pulse width. Specify label name as pulse width, label type as ROI, and data type as numeric. The label definitions appear in the Label Definitions browser. Create custom auto-labeling functions. Use 4 custom labeling functions to label the PRF, bandwidth, duty cycle, and pulse width. Code for these functions is given in the Supporting Functions section of the example. To create each function, on the Labeler tab, click Automate Value and select Add Custom Function. Signal Labeler shows a dialog box where you input the name, description, and label type of the function. For the function that computes the PRF, enter Compute PRF in the name field and select Attribute as the label type. You can leave the description field empty or you can enter your own description. For the function that computes the bandwidth, enter Compute Bandwidth in the name field and select Attribute as the label type. You can leave the description field empty or you can enter your own description. For the function that computes the duty cycle, enter Compute Duty Cycle in the name field and select Attribute as the label type. You can leave the description field empty or you can enter your own description. For the function that computes the pulse width, enter Compute Pulse Width in the name field and select ROI as the label type. You can leave the description field empty or you can enter your own description. If you already have written the functions, and the functions are in the current folder or in the MATLAB path, Signal Labeler adds the functions to the gallery. If you have not written the functions, Signal Labeler opens blank templates in the editor for you to type or paste the code. Save the files. Once you save the files, the functions appear in the gallery as shown in the figure 4. Label waveform type, PRF, bandwidth, duty cycle, and pulse width. Set the waveform type of each signal. 1. In the labeled signal set members, select the checkbox next to radar data 1. 2. Click the Display tab and select Spectrogram in the Views section. The app displays a set of axes with the signal spectrogram and a spectrogram tab with options to control the view. 3. Click the Spectrogram tab, select the Time Resolution section and set the overlap percentage to 99. 4. The spectrogram shows that the signal waveform is rectangular. In the Label Viewer attribute table, double-click the cell below Waveform Type and type rectangular. 5. Repeat this manual labeling step for all the signals in the data set. In this slide we will see Figure 5, an example of a rectangular waveform. In this slide we can see Figure 6, an example of a linear FM waveform. In this slide we can see Figure 7, an example of a stepped FM waveform. Compute and label the PRF of the input signals. 1. Select PRF in the Label Definitions browser. 2. In the Automate Value gallery, select Compute PRF. 3. Click Autolabel and select Autolabel all signals. In the dialog box that appears, click OK. Repeat the above steps for bandwidth, duty cycle, and pulse width by selecting the corresponding label definition and autolabeling function. Signal Labeler computes and labels all signals, but displays labels only for the signals whose checkboxes are selected. Plot the signals from the first 5 members. In this slide, you can see the Signal Labeler window, which is a powerful tool for analyzing radar signals. On the left side, we have the Label Definitions panel, where we've defined labels for various signal characteristics, such as waveform type, PRF, pulse repetition frequency, duty cycle, bandwidth, and pulse width. These labels help us categorize and analyze the different aspects of the radar signals. Below that, in the Labeled Signal Set Members section, you can see the signals that have been imported into the tool. For each signal, we've computed and labeled the key characteristics. For example, the signal named radardata1.mat is shown with a rectangular waveform type, a PRF of 10,000.87 Hz, a duty cycle of 0.50007, and a bandwidth of 2,91,132.44 Hz. The pulse width for this signal is also displayed along with its associated value. On the right side of the slide, you can see the visual representation of the signals. The top graph shows the real and imaginary parts of the signals plotted against time. This visualization helps us see how the signal behaves over time, which is essential for understanding its characteristics. At the bottom right, we have a table that summarizes the computed characteristics for multiple signals. This table includes information such as waveform type, PRF, duty cycle, bandwidth, and pulse width for each signal. This is particularly useful when you need to compare multiple signals side by side. Validate labeled signals. View your labeling progress and verify that the computed label values are correct. Select Waveform Type in the Label Definitions browser and click Dashboard in the Labeler tab. The plot on the left shows the labeling progress, which is 100% as all signals are labeled with the waveform type label. The plot on the right shows the number of signals with labels for each label value. You can use the label distribution pie chart to assess the accuracy of your labeling and confirm the results are as expected, as shown in the figure 9. Next, validate that all pulse width label values are distributed around 5e⁻⁻5. To look at the time distribution of the pulse width label values, click Definition Selection on the Dashboard tab and select Pulse Width. Click on the time distribution plot and on the Dashboard tab, set bins to 3, xmin to 4e⁻⁻5 and xmax to 6e⁻⁻5. All signals have a pulse width distributed around 5e⁻⁻5 as shown in figure 10. Export labeled signals. Export the labeled signals to train AI models. On the Labeler tab, click Export and select Labeled Signal Set to File. In the dialog box that appears, give the name radar data lss.mat to the labeled signal set and add an optional short description. Click Export. Go back to the MATLAB command window. Load the labeled signal set and create signal and label data stores from the labeled signal set. Create a combined data store with the signal and label data stores. Use read or read all to get signalable pairs that you can use to train AI models. Supporting functions. Compute PRF function, calculate the pulse repetition frequency. The compute PRF function computes and labels the PRF of the input signal. It uses the pulse period function. We will see the line-by-line explanation in next slides. Function declaration. Function, label val, label LOC, is equal to compute PRF of x, t, parent label val, parent label LOC varar again. X, the signal data, likely representing a radar pulse. T, the time data corresponding to the signal. Parent label val, parent label LOC, these are additional inputs that could be used for labeling, though they are not utilized in this function. Varar again, a variable length input argument list, not used in this function, but allows for flexibility in passing additional arguments. The function returns two outputs. Label val, the calculated pulse repetition frequency, PRF. Label LOC, an empty array, which could be used to store the location of the label, though it's not utilized here. If tilde is real of x. This line checks if the signal x is complex. The tilde operator is used for logical negation, so tilde is real of x returns true if x is not a real number, therefore, if it has imaginary components. X is equal to abs of x. If x is complex, this line takes the absolute value, magnitude, of x. This is important because the pulse repetition frequency calculation typically requires the magnitude of the signal, not the complex values. PRI is equal to pulse period, xt. This line calls a function named pulse period, passing x and t as arguments. The function pulse period, presumably defined elsewhere, calculates the pulse period, PRI, of the signal x. The pulse period is the time between consecutive pulses in the radar signal. The result is stored in the variable PRI. It is likely that PRI is an array containing multiple pulse periods, with PRI of 1 representing the first pulse period. Label val is equal to 1 by PRI, 1. This line calculates the pulse repetition frequency, PRF, by taking the reciprocal of the first pulse period, PRI, 1. The PRF is essentially the frequency at which the radar pulses are transmitted. It's computed as the inverse of the pulse period because frequency is the inverse of time. The calculated PRF is stored in the output variable label val. Label LOC is equal to empty array. This line initializes the output variable label LOC as an empty array. Although this variable is part of the function's output, it isn't used in this specific function. It might be reserved for future use or required by the function signature for consistency with other labeling functions. Summary. This function is designed to calculate the pulse repetition frequency, PRF, of a radar pulse signal. The main steps involve checking if the signal is complex and converting it to its magnitude if it is, calculating the pulse period using the pulseperiod function, computing the PRF by taking the reciprocal of the pulse period, returning the PRF as label val and an empty array as label LOC. The purpose of this function is likely to be used in a larger framework for labeling and analyzing radar signal characteristics, particularly focusing on the PRF, which is a critical parameter in radar systems. Compute bandwidth function, calculate the pulse bandwidth. The compute bandwidth function computes and labels the bandwidth of the input signal. It uses the OBW function. We will see this code explanation in next slides. Function declaration. Function, label val, label LOC, is equal to compute bandwidth, x, t, parent label val, tilde, var argin. This line defines a function named compute bandwidth. The function accepts several inputs. X, the signal data, typically representing a radar pulse. T, the time data corresponding to the signal. Parent label val, a parent label value, not used in this function. Tilde, a placeholder indicating an unused input, likely parent label LOC in the function signature, which is a way to ignore that input. Var argin, a variable length input argument list, not utilized in this function, but allows for additional arguments to be passed if needed. The function returns two outputs. Label val, the calculated bandwidth of the signal. Label LOC, an empty array, which could store the location of the label, though it's not used in this function. If tilde is real of x. This line checks if the signal x is complex. The tilde operator negates the logical result, so tilde is real of x returns true if x has imaginary components. X is equal to abs of x. If x is complex, this line takes the absolute value, magnitude, of x. The function requires the magnitude of the signal to accurately calculate the bandwidth. Fs is equal to 1 by mean of diff of t. This line calculates the sampling frequency Fs of the signal. Diff of t computes the differences between consecutive time points in the t array. This gives an array of time intervals between each sample. Mean of diff, t, takes the average of these time intervals, giving the average time between samples. 1 by mean of diff of t calculates the sampling frequency Fs, which is the inverse of the average sampling interval. This value is necessary for determining the bandwidth of the signal in the frequency domain. Label val is equal to OBW of x, Fs. This line calculates the occupied bandwidth of the signal x using the OBW function in MatLab. OBW of x, Fs, computes the bandwidth of the signal x based on the sampling frequency Fs. The occupied bandwidth is defined as the frequency range within which a specified percentage of the signal's power is contained, typically 99%. The calculated bandwidth is stored in the output variable label val. Label LOC is equal to empty array. This line initializes the output variable label LOC as an empty array. Although part of the function's output, it's not used in this function. Like the previous function, this might be reserved for future use or for consistency with other labeling functions. Function signature. Label val, label LOC, these are the output variables. Label val will store the calculated duty cycle value. Label LOC is an output related to the location or time indices of the duty cycle but is not used here. X, the input signal, likely a radar pulse. T, the corresponding time vector for the signal x. Parent label val, this is an input parameter that might be passed from a parent function or script. It isn't used in the function itself but might be relevant for a larger context. Parent label LOC, similar to parent label val, this parameter might be used in a larger context but is not used within the function. Var argin, this stands for variable length input argument list. It allows the function to accept additional input arguments if needed. However, in this function, var argin is not used explicitly. As discussed earlier, this part of the code is used to check where X is complex valued signal or not. If the signal X is complex, the code takes the magnitude, absolute value, of X. The magnitude of a complex number represents the distance from the origin in the complex plane, which is often used to convert complex signals into real-valued signals. Label val is equal to duty cycle of X, t. This line calculates the duty cycle of the signal X over time t using MATLAB's built-in duty cycle function. The duty cycle is the ratio of the pulse width, the time the signal is on, to the pulse period, the total time of one cycle, including both on and off times. The result, label val, is a value between 0 and 1 representing the fraction of time the signal is on. This line sets label LOC to an empty array. In this specific function, label LOC is not used, so it's simply initialized as an empty array. Compute pulse width function, calculate the pulse width. The compute pulse width function computes and labels the pulse width of the input signal. It uses the pulse width function. We will see detailed explanation in next slides. Function signature. Label val, label LOC, these are the output variables. Label val will store the calculated pulse width value. Label LOC will store the indices or locations in the time vector t corresponding to the start, IC, and end, FC, of the pulse. X, the input signal, likely a radar pulse. T, the corresponding time vector for the signal X. Parent label val, this is an input parameter that might be passed from a parent function or script. It isn't used in the function itself but might be relevant for a larger context. Parent label LOC, similar to parent label val, this parameter might be used in a larger context but is not used within the function. var argin, this stands for variable length input argument list. It allows the function to accept additional input arguments if needed. However, in this function, var argin is not used explicitly. PW, IC, FC, is equal to pulse width, X, t. This line uses MATLAB's built-in pulse width function to calculate the pulse width of the signal X over the time vector t. PW, pulse widths of the signal. IC, index or time corresponding to the start, initial, of the pulse. FC, index or time corresponding to the end, final, of the pulse. The pulse width function finds the duration of the signal's high state, where the signal is considered on. If the signal has multiple pulses, it will return a vector of pulse widths, and IC and FC will be vectors corresponding to the start and end of each pulse. Label val is equal to PW of 1. This assigns the first pulse width value from PW to label val. If the signal has multiple pulses, the function only returns the width of the first pulse. Label LOC is equal to IC of 1, FC of 1. This creates a two-element vector label LOC that contains the start, IC, 1, and end, FC of 1, times or indices of the first pulse in the signal. Summary. The function starts by converting the input signal to its magnitude if it is complex. It then calculates the pulse width of the signal using MATLAB's pulse width function. The width of the first detected pulse is stored in label val, and the corresponding start and end times or indices are stored in label LOC. This function is likely used within a larger framework for analyzing radar signals, where various characteristics such as pulse width, duty cycle, and bandwidth are being computed and labeled. Conclusion. In this presentation, we explored the complete process of importing data into the signal labeler and defining various labels for key radar signal characteristics such as waveform type, PRF, bandwidth, duty cycle, and pulse width. We discussed how to create custom auto-labeling functions to streamline the labeling process and ensure consistency across datasets. We also demonstrated how to validate the labeled signals, ensuring that our data is accurately annotated for further analysis. Finally, we covered how to export the labeled signals for use in other applications or further processing. Supporting functions such as compute PRF, compute bandwidth, compute duty cycle, and compute pulse width were also introduced, providing the necessary tools to automate and enhance the signal labeling process. By following these steps, we can achieve efficient and accurate radar signal analysis, paving the way for advanced signal processing tasks. Thank you friends and meet you in next video. Bye.